Here's another sample problem on using the following equation: F equals ILB, F equals ILB sine theta, which in the vector form it's IL cross B. Remember what this means. If you have a magnetic field and magnetic field points like this, B, and then you have a wire that runs through this magnetic field like this, and there's a current I in this wire. The angle is formed between the magnetic field and the current I, and that's the angle theta. Length L is the length of the wire in the magnetic field, and so that just be this L. All right, now let's try a problem. Here's another one. This one is on page 826, number 33. Again, this is in the algebra-based textbook. And so what do we have here? We have 3 wires. What is the net force on each wire and following? All right, let's try it. So we have 3 wires, and I think I might need to draw this big enough. So let's say here's one wire. It goes like this. Here's another wire. And here's another wire, and each one of them is carrying a current I. Right, so I have 3 of these. Now the directions of the current. So I have 10, 10, and 10 amps for each one, but this way, and that way. Okay, so I have a current I here that is 10 amps. It flows in this direction. Here I have a current I that is also 10 amps, but it flows in the opposite direction. And here I have a current I that is also 10 amps, but it flows in this direction. And you have some geometry with it. That is, you know that you have 2 centimeters for space here. So let's draw that. So what I have here is 2 centimeters. So this is 0.02 of a meter. And I have this distance being the same. This is also 0.02 of a meter. And the question is, what is the net force on each wire? Now I'm not going to do each wire, I'm just going to do one of them. So I'm going to do the middle wire. So what's the net force on the middle wire? What is the net force on this wire here? Right, what's the net force on this wire? Let me state this here. Find F net on wire 2. And so I'm going to label these wires. This is going to be wire 1. It's going to be wire 2. This is going to be wire 3. And in this sense, I'm going to have the first current I1, second current I2. I'm going to have third current I3. All right, let's see if we can understand the picture here. Well, what kind of a force is acting on this wire, wire 2? Well, it would be magnetic force. But if it is to be a magnetic force, then that force must come from the magnetic field. And where is the magnetic field coming from? Well, there's the magnetic field here at the location of this wire that is set up by the wire above and by the wire below. Recall, I'm going to draw this on the side, that if you have a current that flows like this, current I, and this current, using a right-hand rule, a different right-hand rule, but using a right-hand rule, will flow. This current was going to set up its own magnetic field at points like this. Here's the magnetic field from this one. Likewise, if you have a wire and then the current flows in it in this direction, then you're going to end up with a magnetic field that points like this, rolls around. So, and so there's a magnetic field here produced by one wire and produced by the second wire. So let's draw it here. Using the other right-hand rule, I would have the magnetic field here that does something like this. all the way there, and then it points into the page here. So the magnetic field due to wire 1 points into the page at the location of wire 2. So I'm going to draw X here. I'm going to label this as B1 because it is due to I1. Likewise, the magnetic field produced by wire 3. So use your right hand, the first right hand rule, that is, take the thumb of your right hand, make it point to the right, curl your fingers, and you will find out that the magnetic field here points like, oh, that's going to be tricky to draw. Well, it goes under the wire on the other side and comes out of the page on the top. So it's coming out of the page here. I'm going to draw it like this. This would be B3. I'll label this as B3 because it is due to I3. If I were to draw it a little differently, that is, let me draw it like this. It's the same picture, but it's from a different perspective. So I have the first wire with the current I1 coming at me, I1. I have the second wire with the current going into the page, that's I2. And I have the third wire with the current coming at me out of the page, that's I3. See what I did? I rotated this whole picture in such that I have a different perspective. I'm looking into the wires. I'm not looking at the wires from the side now, but rather I'm looking into these wires. And so I1 comes at my face, I2 goes away from my face, I3 comes at my face. Now let's draw the magnetic fields produced by these wires. So the wire on the top, this current I1, is going to set up a magnetic field that points like this. Wait, let me do this with my hand. So the thumb points at my face and I curl my finger. So I'm going to get a magnetic field that does this. I actually want to draw it bigger. Oh, why not? Let's draw it like this first. This would be the direction of this field. But I need it a little bigger here, such that it extends to this point here. So I'm going to get something like this. And this would be B1. It points at this wire here. And this is what I meant by saying that the magnetic field here points into the page. All right, so this here is represented by this here. Now this one points just the same thing. That is, I get this magnetic field that points like this. Right, so there's that. But I need a little bigger. So now what I'm going to do is I'm going to draw it like this. Goes all the way around and comes back and it points in this direction. So this is now B3. B3 because it is due to I3. But they point in opposite directions here. And this picture here is what I tried to draw here with that. In any event, what I see is that the magnetic fields at the location of I2 oppose. So I can find the force on this wire by using the following equation, just the force equation. So the force equals I, and it would be I2, times the length of the wire, whatever the length of the wire. Do I have the length of the wire in this problem? Yeah, 50 centimeters. Okay, well, I'll add that later. But anyway, so I have F on the wire, on the middle wire, would be I2 times the length of this wire times the net magnetic field. So the net force on my wire would be all of that times the sine of 90 is what I would have here. So this is just sine of 90, right? Because 90 is the angle between the magnetic field B and the current I. Magnetic field points to the right or to the left, and then the current itself points into the page. That's 90 degrees, and so I have sine of 90. In other words, F net equals I2 times L times B net. Let's plug in some numbers here. F net equals I2, that was 10 amps times length. I didn't state this before, but the length L was given to us in this problem. And so length L of the wire here was 50 50 centimeters. So we have 0.5 of a meter. That's my length L. I'm going to put here times 0.5, then times B net. Well, B net is going to be the difference between the two magnetic fields. So I have to calculate the two magnetic fields and actually then figure this out. So B1, calculate B1. So this is good. I just have to figure out B net. So B1, which is the magnetic field produced by I1, is going to be, now we have to look up the equation for that. So it's mu net times I1 over 2 pi times R. Now R is the distance from the wire to my point of interest. So this is R, and I'm also going to draw it here. This would be my R. That of course is just 0.02. So I can easily calculate this. This would be 4 pi times 10 to the minus 7th over 2 pi times I1 was 10 amps divided by R 0.02 equals. So this goes away, this goes away. I have 2 and 2, so that actually will take care of that part. I have 10 here, but then I multiply it by 100 because of that. So what I have is 1000. So this will be 10 to the minus 4th Teslas. That's B1. B2, rather B3, the way I labeled it, would be mu net times I3, that's 3, divided by 2 pi R equals, and so this gives me 4 pi times 10 to the minus 7th over 2 pi times I3 is 10 over 0.02. And that you will see is exactly the same thing. So pi goes away, 2 and 2 goes away with 4, and up with the same thing. So this is 10 to the minus 4th Teslas. In other words, magnitudes of B1 and B3 are the same, but they point in opposite directions. And B net is the difference between them. B net is B1 minus B3, right? They point in opposite directions. So they give me 0 Teslas at that middle location. And that implies that the net force on the middle wire is just going to be 0 newtons. Oh, so much work for nothing. All right, now you should continue and figure out the net magnetic force on the first wire. What is that? And then the net magnetic force on the third wire. And the net magnetic force on these two, the third wire and on the first wire, is not going to be 0.